Okay, so hello everyone. In this video we will cover deadlock. So in this video we will first discuss that what is deadlock, and then we will see RAG, resource allocation graph in deadlock, and then we will see that how to solve questions on single instances and multiple instances RAG. So moving forward to deadlock. So what exactly is deadlock? Deadlock is a situation where two or more processes are waiting for an event to happen, but that event never actually occurs. This leaves all the processes stuck in a waiting state infinitely. Those processes are then said to be in a deadlock state. Let me explain this concept with a simple example. Imagine you want to open a bank account. You go to the bank and tell the bank personnel that you want to open an account, but the bank person says first you have to deposit this minimum amount and then we will open this account. However, you respond by saying that first I will open the account and after that if I want I can submit the money. Now what is this? This is a deadlock situation. Why? Because what you are saying is that you will definitely give the money, but you want them to open the account first. But what the bank person is saying, it is saying that you must first deposit the money, then we will open the account. So both parties are waiting for an event to happen, but that event will never occur. That's what we call a deadlock situation. Let me give you another example that happens quite commonly. Consider two cars A and B with two drivers driving those cars. Driver A is saying that he is on the right direction and moving in the lane. At the same time, driver B is also moving towards A from the opposite direction. Let's say that B is driving on the wrong side. In this situation, what will happen? Both are waiting for some event to occur. What is an event? Driver A says that he want to go in his direction and driver B is also saying he want to go to his direction. But how will they both go? Either A will have to reverse back his car or B will have to reverse his car. Neither A will remove his car nor will B remove his car. So what is this? This is a kind of deadlock situation where both are completely stuck. Now, if we talk in technical terms, especially in synchronization, we also encounter deadlock situation. Like when there are two semaphores S1 and S2, there is a process P1 that wants both semaphores S1 and S2 complete its execution, and there is another process P2 which also want S2 and S1. So let's say that P1 has acquired semaphore S1 and is waiting for S2, while P2 has acquired semaphore S2 and is waiting for S1. So what happens here? This is again a called of like deadlock situation, because P1 got one semaphore S1 but didn't get the S2. Why didn't it get S2? Maybe because it went to sleep or got preempted, so P2 got the chance and acquired S2. But when P2 was trying to get S1, it also went to sleep, which means control went back to P1, and so P1 has S1 and says I want S2, and P2 has S2 and says I want S1. So both are waiting for an event to happen. What is the event? P1 getting S2 and P2 getting S1, but they won't get their resources because P1 made S1 unavailable by acquiring it and P2 made S2 unavailable, and both are now in a blocked state. Now who will unlock them? Nobody will unlock them. This is called a deadlock situation. Now let's see with the example, resource example. Suppose there are two resources R1 and R2 and two processes P1 and P2. Let's say that R1 is allocated to P1. This line shows that P1 has taken R1. P1 is also requesting R2, because we can see P1 is asking for R2 and R2 is held by which processes? P2, while P2 is requesting R1. So what is this situation? This situation looks like a deadlock, but we can't call it deadlock yet, because for a deadlock to occur there are four necessary conditions that must be met. What are the conditions? These conditions are mutual exclusion, no preemption, hold and wait, and circular wait. These four are necessary conditions. If any of these four conditions does not get satisfied, then there will be a chance that deadlock may not occur. So that's why understanding this condition is very important. First condition, mutual exclusion. The mutual exclusion means that whatever resources you are using in the system, that resource must be used in a mutual exclusive manner. This means it should not happen that more than one process can use that resource at the same time. Now take a printer as an example. If there is a process that is using the printer to print something, and at the same time another process came along and the first process will not be preempted or stopped, it's not like the second process pages are also printing while the first process pages are printing, both printing simultaneously. No, this should not be happen. The resource must be used by one process at a time. Interleaving or concurrent usage is not allowed. So mutual exclusion means that whatever resources you are using, all the resources must be used by all the processes in mutually exclusive manner, one by one. Now the second condition is no preemption. No preemption means that if P1 is using R1, R1 is allocated to P1 and P1 is requesting R2 while P2 is requesting R1, then preemption should not occur. What does preemption mean? Preemption mean it should not happen that one process is holding some resources and another process comes and forces the first process to release its resources. No, this should not happen. Preemption will not be there, which means there is no priority system where if a high priority process comes, then a low priority process is forced to give up its resources. We are talking about equal priority process here. So that's why preemption will not occur. A process which is holding a resource will keep holding it until it completes its execution. It will not be preempted. Now the third condition is hold and wait. Hold and wait is exactly what we see in our example. Hold and wait means P1 is holding one resource, that is R1, and what is the another resource? R2, and P2 is holding one resource, that is R2, and waiting for another resource R1. So this is the hold and wait condition. It should not happen that P1 says I want R2 and then release R1. So a process holds one or more resources that it already has and wait for other resources that it doesn't have but need for execution. So this is what? This is third condition, hold and wait. Now fourth condition is what? Circular wait. Circular wait means there is a kind of circle or loop in the resource dependency. This create what we call a cycle. If there is a loop or cycle in the system, then definitely a lock situation can occur. I am still saying that it can occur because all four conditions are very important. Only after checking all four conditions we decide whether deadlock is actually present or not. Let's see one more example of circular wait. Suppose there is a process P1 which is holding some resource R1. There is a process P2 which is requesting R1. P2 is holding some resource R2. Let's say there is another process P3 which is requesting R2 and it is holding R3. So P3 has R3 and it is waiting for R2, and P1 is holding R1, it is requesting resource number R3. So let's see the circular wait here. P3 is having R3 and waiting for R2, P2 is having R2 and waiting for R1, P1 is having R1 and waiting for R3. So this creates a kind of circular wait, a loop comes here. So these four conditions are necessary condition which we also call necessary and sufficient for a deadlocked situation to occur. Not just one condition alone: mutual exclusion, no preemption, hold and wait, and circular wait. If all four necessary conditions are present, then we can say deadlock is occurring. Now let's talk about resource allocation graph. Resource allocation graph is the most efficient and convenient way to present the state of the system. It shows how resources are allocated to processes and how processes have been assigned multiple resources in our system. To represent this, we use the resource allocation graph, which is also known as RAG. If we want to determine whether there is a deadlock in our system or not, RAG is the most suitable method for representing and analyzing this. Like any normal graph, RAG also has two main components, vertical and edges. In verticals in RAG, there are two types: process vertex and resource vertex. Whatever number of processes are running in our system, all the processes are represented with circles. Resources, whatever resources we have in our system like CPU, register, memory, monitor, printer, or any other resource in our laptop, mobile or tablet, we represent them using rectangles. Now types of resources. Resources are of two types: single instance and multiple instance. In our system, there can be resources which exist only once. This is present as a single instance like CPU or monitor. Generally in our system we have one CPU and one monitor, but some resources are present in the multiple numbers. They have multiple instances like registers. We can have more than one printer connected with our system, so that can be a multiple instance resources. Now edges in RAG. Edges represent two things: assigned edge and request edge. An assigned edge means when a resource is connected to a process, and if there is an edge which is moving towards the process, it means that resource is assigned to that process. In other words, that process has already taken that resource. A request edge is represented when the arrow is going towards the resource. When an edge goes from the process towards the resource, we call it an request edge. This means the process is requesting that resource. So if we have R for resource and P for process, then when an arrow goes from R to P, it means the resource is assigned to the process. When an arrow goes from P to R, it means the process is requesting the resource. Now moving forward to the example of single instances RAG. Let's say we have two processes P1 and P2. We represent processes with circles and resources with rectangles. Both are vertices. We have two single instance resources R1 and R2. This example deals with single instance resources, meaning we have only one instance for R1 and only one instance for R2. You can think of R1 as CPU and R2 as monitor. So what does this diagram represent? P1 has been assigned R1, This is shown by the arrow going from R1 to P1, but P1 is requesting R2. This is shown by the arrow going from P1 to R2, and P2 has been assigned R2 and shown by the arrow from R2 to P2. There is also an edge from P2 to R1, which means P2 needs R1. So this is how we represent a normal REG. Now what is the advantage of representing it this way? The main reason is that we need to check whether there is a deadlock in this system or not. This is most commonly asked question in GATE exam or other competitive exam. When you will be given REG and you have to determine whether deadlock exists or not by analyzing that REG. Let's examine the first example. This creates a circular weight, and circular weight is one of the necessary condition of deadlock. So yes, there is a circular weight, there is a cycle. A cycle means if we start our journey from R1, can we come back to R1? Yes, we can come back to R1. That is called a cycle. But let's analyze this more systematically. We can create a table to analyze this properly. We have two processes, P1 and P2. We have two resources, R1 and R2. Let's create an allocation and request table. Let's check availability. How many resources do we currently have available? R1, is there any resources for R1 available? No. Do we have any resources for R2 available? No. So availability is 0. So our current availability is 0 for both R1 and R2. Now looking at this availability, can we fulfill any request? Can we fulfill the request of P1 or P2? No. So neither can we fulfill the request of P1 nor can we fulfill the request of P2, because our current availability is 0 for both resources. In this situation, you can clearly say there is a deadlock situation. Now example 2. Let's solve a second example to understand the difference. Suppose we have three processes, P1, P2 and P3, and two resources, R1 and R2. Looking at this REG, P1 is allocated to R1 but is not requesting anything. P2 is allocated to R2 but is not requesting anything. P3 is not allocated any resources but it requesting R1 and R2 both. Now what is the current availability? R1 is equal to T0, R2 is equal to 0. Both are allocated. Can we fulfill any request? Now here is the concept. P1 is requesting nothing, so P1 can execute successfully. When P1 terminates, it release R1. New availability become R1 is equal to 1, R2 equal to 0. P2 is also requesting nothing, so P2 can execute. When P2 terminates, it release R2. New availability becomes R1 equal to 1, R2 equal to 1. Now P3 needs both R1 and R2 and we have both available, so P3 can execute successfully. So all processes can complete execution. Is there a deadlock? No, there is no deadlock, but there is an important distinction here. P3 will wait for some time because it needs resources that are currently allocated to other processes. When will P3 get the resources? After P1 and P2 completion. P1 and P2 will complete after some finite amount of time. So P3 knows that after some finite amount of time, it will definitely get executed. This finite waiting is called starvation, not deadlock. Now, is there a circular wait in this example? Let's check. If we start from P1, can we come back to P1? No. So we can say this graph is acyclic. There is no cycle. This gives an important rule for a single instances system is if REG has a circular wait cycle, there will be always a deadlock. If REG has no circular wait, no cycle, there will be no deadlock. But this rule is truly for single instance resource system. Now we are moving forward to multiple instance REG. Now let's discuss multiple instance REG where resources can have more than one instance. We are taking an example here. Let's solve an example with multiple instance resources. Suppose we have three processes, P1, P2, P3, two resources, R1, single instance, R2, two instance. Looking at this REG, P1 is allocated to R1 and requesting R2, P2 is allocated to one instance of R2 and requesting R1, P3 is allocated one instance of R2 and requesting nothing. So you can see there is a circular wait here, P1 to R2, R2 to P2 and P2 to R1, R1 to P1. So there is a cycle in the graph, but let's analyze systematically. Now allocation is what? P1 R1 is equal to 1, R2 is equal to 0, P2 R1 is equal to 0, R2 is equal to 1, P3 R1 is equal to 0, R2 is equal to 1. Now what is the request? Request is P1 is equal to R1 is equal to 0 and R2 is equal to 1, and for P2 R1 is equal to 1, R2 is equal to 0, P3 R1 is equal to 0, R2 is equal to 0. So current availability is R1 is equal to 0, R2 is equal to 0. Can we fulfill any request? Yes. P3 is requesting nothing, so P3 can execute. When P3 terminates, it releases one instance of R2. R2. Now P1 needs one instance of R2 and we have one available. So P1 can execute. When P1 terminates, it releases R1, and now P2 can get the R1 it needs and execute successfully. So even though there was a cycle, there is no deadlock because all process can eventually complete. This teaches us important lesson. In multiple instance system, the presence of a cycle does not guarantee a deadlock. For single instances system, cycle means deadlock always, but for multiple instance system, we must perform the complete systematic analysis. Now we will see another example. This is an important example, a gate question. Let's solve a more complex example that was asked in gate exam. We have four processes P0, P1, P2, P3, three resources R1, 2 instances, R2 3 instances, R3 2 instances. This diagram looks very complex, so manual analysis would be difficult. That's why we follow the systematic method. Let's fill our tables. Allocation metric is what? P0 R1 is equal to 1, R2 is equal to 0, R3 is equal to 1. Now P1 R1 is equal to 1, R2 1, R3 0. P2 R1 0, R2 2 1, R3 0. And P3 R1 0, R2 1, R3 0. And what is request matrix? For P0 R1 is 0, R2 1, R3 1. And for P1 R1 1, R2 0, R3 0. For P2 R1 0, R2 0, R3 1. And for P3 R1 is 1, R2 is 2, and R3 is 0. So what is the current availability? Current availability is R1 is equal to 0, R2 is equal to 0, R3 is equal to 0. Now what is the analysis? P2 needs only R3, so R3 is equal to 1 and we have R3 is equal to 1 available, so P2 can execute. After P2 terminate, new availability will become R1 0, R2 1, R3 1. Now P0 needs R2 1 and R3 1 and we have the both available, so P0 can execute, and after P0 terminate, new availability will be R1 is equal to 1, R2 1, R3 2, and P1 needs R1 1 and then like we have it available, so P1 can execute. After P1 terminate, new availability will become like R1 2, R1 2, R2 2 and R3 2. Now P3 needs R1 1 and R2 2, so and we have this sufficient resource, so P3 can execute. Now execution sequence is P2, P0, P1 and P3. First P2 will execute P0, then P1, then P3. Since all the processes can complete execution, there is no deadlock in this system. Now let me summarize the key principle we have learned. Like for single instance system, if RAG contains a cycle, there will always be a deadlock. If RAG contains no cycle, there will be no deadlock. Cycle detection is sufficient for deadlock detection. For multiple instance system, a cycle is necessary but not sufficient for deadlock. Even if a cycle exists, deadlock may not occur. So that's it for this video. We will meet in next video. Until then, bye bye.